begin today's one. So how many of you did the homework?
All of us.
All of us.
I tried.
Including Nigel. Okay, good. So, did you get something like this? Yes. Good.
I did not, because I stopped it like once frog levels, or was it mosquito, whatever the level reaches 0, and then it becomes a straight line after 0.
Okay. Okay.
Pretend this is something that's not.
Yeah.
Okay.
No,
Because I
that's
was like, you can't get -1 frog or
Okay.
something like that.
Can be the rates
Cool.
or something.
So, I mean, I'll kind of talk a little bit. Put some on. I'll talk a little bit about this. So, you can get negatives actually. So, I'll put this. Maybe do this here. There's a 0 here. So that means you can see. So you see first, we see the frog's level going from 0, and the mosquito starting at 100. And after a bit of time, you have this decay of the mosquitoes going down, and you have the frog level going up because of this factor here. So it's depending on how many mosquitoes there are. And the frog levels mosquito levels are going down because of this term. They're getting eaten by the frogs. Make sense? Yeah. We also have this decay term here. Then after a while, you see that you get this negative effect because this is remember this is population with respect to the mean. It's not the actual absolute value. So you get below minimum value, below the 0 value. And then you have this rebound effect. It goes all the way back up. So all of a sudden, you can now get generation of mosquitoes. And the reason why that happens is because of this term here. So as you can see, it's minus 0.5y. So if y is negative, if the itself mosquitoes are negative, this turns to a plus, which means this rate of change goes positive. And the reason why you have that, you have in this case because it means it's decaying, but you also have this term to correct, to say you don't have to decay forever. You kind of generate more and more mosquitoes. And you go back to the actual mean level of mosquitoes, which is 0 at the end. Because remember, this system only kind of talks about the deviations from the mean, and we started with a deviation. We added 100 at the start. We look at the response to that. Yeah? Cool. Did anyone play around with the model? Or did you just do it and like, it's done? Okay. So I suggest, I mean, if you still have to do it, I just play around with it. Just it's sort of nice to play around with it, and you'll kind of understand why I asked you to do that. And we'll play around with something, a newer model, we can tweak the parameters in a couple of lectures' time. So another thing you can do, if you do tweak it though, if you change this term here, so the rate of decay of the mosquitoes dying to 1, so it's stronger, you have this faster decay of the mosquito population. It decays much, much faster. And because of that, the number of frogs doesn't reach 140, it reaches just above 80, the peak. And decays much, much slower because these guys are all gone. That's the thing, if you tweak these parameters, if you change kind of the state-dependent coupling, you have this change dynamics. The last one here is a more interesting case, is if I change now the rate at which mosquitoes are being eaten. So I've changed this 0.1 factor to 0.2. So it's double, they're getting even twice the rate. And so because you have that, you have this rebound effect and this oscillation now. With this, you have this, in the system before we had none of this term, we just had 2 terms, if you remember, with oscillation. So we started the activities that are key happening. But you also have this envelope of decay. This effect gets weaker and weaker and weaker. So this is something I think that you should be playing with. So go back after today and just have just play the terms, just change the terms in front, to see how all these things interact. Yeah, because these are like the basics of differential equations and the basics of dynamics. Really, kind of use all these effects in this sort of unit oscillation and in DCM. Okay, so on board. Now, what I want to do is talk a little bit more about this system, but I'm going to introduce some extra effects into here. So, just to clarify again, we had oscillations, these upper effects, we had decay, and we have rates of change. So we almost have everything we need for DCM, all the tools, all the bits and pieces we need. The last thing we have to add in now is to add in inputs. So as I said before, we started with an input at the start, with 100, and we let it go, let the system go. So now, we don't have this passive system, we want to drive the system, okay? So the way we can drive the system is, think of the following scenario. We have all these mosquitoes in this population, and I'm now going to inject more mosquitoes. So the way we can do that, I'll show you a figure. I bought new ones of these. Is if we have so over a small amount of time, I'm going to inject some mosquitoes, and I'll call this injection. I'll call it U. Okay. So I want to add this to the system. And the way I can do that is I can add it with an equation. This is just a Gaussian, that's at 5 days. I can call this the following. UT, this is just the equation for like a normal distribution slash Gaussian. T minus 5 squared divided by 4. Yes, and then we have that times 10. So this will be 10 here. So this is how many extra mosquitoes we're going to do. Okay, so we have this term. This is an input to our dynamical system. So we're going to go about again the same stuff to now solve this system. And I'll show you the effects here. Okay, now how do we put this all in? So we first have the equations. So let's go back to this equation here. So we have dy dt, equals minus 0.1x minus 0.5y. Okay, we're going to do this rates of change. So there should be a plus or a minus in front of the ut. I'm going to add this to the system. Should that be plus or minus, do you think? Minus? Who says minus? For one person who says plus. Okay, so the answer is plus. The reason why is that we're adding this. So the rate of change of mosquitoes, if you want to have more mosquitoes at a certain point, you add a plus. This is why we have the plus.
So aren't there changes in the frogs? So it should have the negative relationship with it.
Yeah, so in fact, this here, so Y is the mosquito population.
The mosquito. Okay.
Yeah, sorry. So that, yeah, sorry. That's why you said that. Makes sense. That makes sense. So the frog population, which will go back to here, is X, and that equals plus Y. Okay?
Sorry, mate, could you not use red?
Red.
I can't see it.
Okay.
It's not
Is that
red.
red on the right hand side there, or is it?
This is
Well,
black.
it is on the right hand side, don't you?
This one here?
Oh, the blue one maybe.
This one here?
Yeah.
That's
Or maybe
blue.
just tilt the board around a little bit with the reflection.
Yeah, maybe the... Better? No. Okay.
Oh,
So,
right.
what I'll do, I'll just do this. I'll do it because you'll need it, because it's part of the homework. There's more homework this week, so make sure you copy all this down.
Actually, if you tilt the board down a little bit, that I reckon will do it.
Like that?
Yeah, a bit more.
Maybe I'll tilt the screen more on your side. That better? No, it doesn't make sense. Okay.
Bracket.
Alright. Can you see that a little bit, Nigel, now? Better?
Not quite still, mate, but that's alright.
Okay. Actually, what I'll do... There. Is that better?
Still not.
Okay. Alright, I'll write this stuff down. So this is, ut equals exp exponential t minus 5 all squared divided by 4. So Gaussian with, send it at 5 divided by 4 times 10. I won't write more in that blue color. It's a bit annoying. Okay. Yep, that's fine. So again, we want to solve it. So how can we solve this? We do the following. Same trick. dy dx, so dt is approximately y of ti plus 1 minus y of ti divided by del t. Yep. Remember from last week. Again, dx dt. Again, let's do the following. X ti plus 1 minus x ti. Cool? Okay, now let's do the following. How would, I want you all to write now and see what you get. What is this? If you rearrange this like I did before, the same thing we did last week, but we now have ut, and ut goes to, you just write uti. What does yti plus 1 equal to? Maybe you should use a pen and paper, don't think in your head. Actually, well, first, we'll keep writing. Maybe we'll start with x, so you get the ball rolling. As soon as you know the answer, shout out, start shouting. Or push them out. They don't have it? Just like we go through it together. Okay, let's go through x of ti plus 1. Okay, that one, if we do the following, if we do, what's it again? X of, so replace this with this one here. X of ti plus 1 minus x of ti divided by delta t equals y of ti. Yep, then we can rearrange and put delta t across, add to the side, it ends up with this one here. Equals x of ti plus 1 plus delta t. So what I did, I just substituted again this term here into this equation here. Yeah? Does anyone have anything for this yet? We can go through it together as well. So we do the same thing as well. We substitute this, or this term here, into this thing here. We do some algebra, and we end up with the following. That equals, oh, let's do that one now. It equals x of ti plus 1 plus delta t y of ti. This one here, it equals, I've got it written down in my cheat sheet, ti plus 1, yep, minus delta t times 0.1 times y of ti plus 1, yep. So in fact, this is the same as what you did last week. You did the same thing as well. That's x, y, ti plus delta t times u ti. Does this look familiar now, this answer?
The first one is yt plus 1.
Oh, sorry, yeah. Ah, see? Hey, you're all listening. Guess you all remember now. Does this make sense now?
Yeah.
Like we had before? It's the same thing? Okay. This is what you do to solve this problem. You can put it through a computer, and you can actually solve the system. Given that's the functional form to start off with. The u of t is equal to exponential 2 minus y squared divided by 4 times 10. Yep. Okay, now, so you should copy this down, because this will be part of your part of your homework. So what I would like to do for your homework is to, same thing you did last week, now have an extra term, delta t times uti. Cool. And I'll put the video on tonight so you can have it all ready if you haven't copied this down properly. Okay.
Should that be XTI as well?
Yep, that's also wrong. Good. Good, Christy. All right. Okay. So the way you want to solve it, we want to make at t equals 0, we want to make y is equal to 0, x equal to 0, and delta t. So we want to solve this system with these conditions. Using the same stuff you did last time. Oh, sorry, 0.1. 0.1. Good. I'm glad you all saw that. And okay, how does this look like? Now, if we put it through a computer, this is what you should get. I'm going to show you the answer, but I want you to do it as well. So what you should get is the following. You should get the frogs to be going up and down. As I saw before, this is the frogs. Or, as you call it, X. What you should also see is that the mosquitoes go up, and they also do this thing there. And this peak should happen, or something around 5. And 10 is a little around there. That's 50. And for clarity, let's also write, I'm going to write this equation here as well. dy dt is equal to minus 0.1 x, 0.5 y, plus u of t, dx dt equals y. So you need this stuff because you'll do an extra additional simulation on top of this. And I just want to reiterate the point. I mean, all this stuff isn't technically needed for DCM in terms of you pressing buttons DCM and just letting it run through. It's all GUI. However, I think it's really ideal for you to understand this in terms of to understand what's happening underneath. And if you want to make simulations to test DCM, I think you really need this. If you want to do any specific, any kind of modeling, these are the steps that all modelers take. Like I would do this if I found a system like this. I would do something like this, and I would solve it, and I would explore parameter space. And papers are made like this. I mean, this can model a bunch of stuff, not just frogs and mosquitoes, but neural oscillations. You can also model any type of population model done with similar type of systems. Quantum mechanics, you can reduce a lot of quantum mechanical forms into something as simple as kind of these simple ordinary differential equations. So it's actually quite powerful. It's not just this Mickey Mouse thing. It's just a real-life research kind of tool. Okay, good. So now we have all that. We have a system which we have oscillations, a system with decay, and a system with drive. Now also there's a language on how to describe all these things and how to actually solve these things. Now a way that we can describe this in a different way is instead of doing this in terms of, everyone finished here? Instead of doing, or representing this by equation, we can represent it by something a bit more familiar. i.e., we can represent this by a kind of connectivity diagram. So, how can we do this? We can have the following. This is our input. And I'm using always boxes for inputs. Input. U of t. This is our increase in mosquitoes. Okay, we have our mosquito population here. Okay, we have our frogs here. Okay, so now we can draw arrows to these things to describe actual processes. So, into the mosquito population, we have this rate of change. We have a positive influence coming to mosquitoes from U of T. And we can call that connection as well. There's 1 in front of there, a hidden 1. It's +1. Okay? So this is now building essentially a DCM, really. Okay, next thing, from the mosquitoes, we have the frogs that eat into the mosquitoes. So frogs' influence on the mosquitoes is, what is it? Negative, -0.1. So we can call that. And you can see I'm only showing, so we have the variable x and y, and I'm only showing the values in front of there. Okay, next one, we have the influences of mosquitoes onto frogs. So we have an arrow here. And if we look at this diagram, this equation here, dx dt, rate of change of frog equals +y +1. Okay? That's it. This here is another form of language. This, or another dialect, you call it. This here, dynamical system, we have these connections, we have these pluses and minuses, and we have this now in a different form. Now this form isn't just specific to DCM, it's specific to a lot of engineering, any type of ODE type system, ordinary differential equations, we have this system. If you look at an engineering textbook, we look at filter design, we look at any type of system, you see this same structure. You have arrows and you have connection weights. This is like this is another dialect in this language, mathematics. Okay, this should look quite familiar to most of you now. Okay, so when you have connections, what else can you do when you have these connections? This type of wiring diagram. What do people normally do? Like if Alex showed you a wiring diagram and put into MATLAB, what would you automatically do at the start?
Initialize the matrix and you put those values.
Yeah, matrix. You make a matrix, right? Connections can be represented in a matrix form as well. We do all these things in a group a lot, of these connection matrices. Okay, so we're going to change this into a connection matrix. Okay, so what I'll do is how I'll do this. Maybe I'll rub this out. Yeah. I'll just redraw it. This part here at the top. Just because we need this just to see in our minds how things are. This is U, this is Y, this is X. Okay, that was +1, that was -1, -0.1. We have that influence the +1. Can anyone see, are we missing any connections here? Cell connection, that's right. So we all do know this stuff. So we have, the way we represent a cell connection is, you can just do this sort of closed loop. This -0.5. Yeah? Okay, so I'm going to show something to you that you all should be very familiar with. So let's say we have region, what do I call this? Region M and region K, and we have two connections, right? In the matrix form, we'll call it A, for starters. If you want to label this connection from M to K, we would call this, we'll call this connection in the matrix entry, we'll call it from, this one here. Wrong way around, wrong way around. From M to K, we'll call it this form. And this matrix we have K regions. So regions this way, we have regions this way. So we would have, for instance, we would have an entry here, A of mk, we're thing here, A of km. So that one will be represented in this connection here, and that one will be represented here. And I'm doing this way on purpose because we normally deal with symmetric matrices where it doesn't matter, you normally have symmetric matrix, the upper triangle looks like the bottom half of the triangle. Yeah, so fluent to everyone. In this case, direction matters. So the K means it's what it lands on, and M, the second one, is where it comes from. Okay, so it's a directed matrix we're going to deal with now. And DCM allows you to calculate these because we have a model to generate these. We also have other connections in these type of matrices too. Like we said, we have self connections. We have here A of M, and here, just to start, for instance, A of KK. So familiar to everyone like that? Cool. Okay, as you can see, we have self connections and we have direct connections. And therefore we can do something with this here. So let's, for our system, we'll call it A here. Now we have Y, these regions. I'm just drawing these as a label, just to guide us. We have A of Y of Y, A of X, Y, A of X, X, and A of Y, X. It's very specific here. So A of Y of X is, so it's 2Y from X. And the other way around is 2X from Y. This order is important here.
I find that counterintuitive. Whenever I see like the A of YX, I think of connection Y to X.
Yeah.
I find that Y coming from X counterintuitive.
It's I think, yeah.
What's the reason for that? Because I notice like connection to which there's a huge split. Some do it.
You usually see IJ, you think of
Yeah.
IS2J.
Yeah. I mean, it depends on, I guess, your style. And in here, there's a reason why it's like that. It's because of the way the DCM works. And when you talk about differential equations, you set up this way. You'll see in a second why it's like that. And it'll be less counterintuitive, hopefully. Maybe, maybe not. Okay, so we have this. Now, what is this matrix equal to? If we look at this wiring diagram, so ignoring U, what is AYY? What's self connection there? Negative 0.5. If we were to scream out this one here, 2Y from X.
Negative 0.1.
Yep. Here, 2X from Y. 1. Last one. 2X from X.
We haven't specified it.
That's it. 0. I've divided it, I've defined it because it's not there. If it's not there, it's 0. That's it. We have now a matrix which represents this wiring diagram. This all should be quite familiar to everyone, I think. Now, the reason why it's this way, you will see now. Okay, I'll leave that there for another second. So, where matrices are actually come from? They come from a series of equations. They always have come from this. So these Gaussian elimination, all this kind of stuff, kind of made these matrices up to solve systems of equations. So now, if I do the following, if I'll call a vector Z, okay, a vector, everyone knows what a vector is? That's right. It's either a row matrix, like one row, or it's one column. So we're going to do a lot with column vectors here. So I'm going to call that Y and X. I'll just read that here. Okay. So now, if I do the following, if I take A and times Z. Now, before I go into that, does anyone know how this works? What this answer will be? This is a matrix, so I can't, it's a little hard to teach this all at once, but I just want to show you what it is, if you're happy with that. Okay, so what that equals to, A of yy, A of yx. And this here, it's a language, it's another dialect. I describe equations. You write this multiplication this way. Okay, this is just how it looks like. Now, the answer to this is, the way you multiply a matrix with a column vector is the following. And I'll show you the trick. The way I know is this way. That times that, plus that times that. That's what you do. And the first one is A, y times y plus, so there, A, y, x times x. That's the first entry of the new column vector at the end. Okay? The next one, we do the same thing. These times together plus these times together. This is just the language of matrices. So if you look at eigenvalue problems, you probably know about eigenvalues and things and eigenvectors. They kind of all have this underlying kind of mathematics in there. So that times that plus x, axx times x. Okay. So by doing this, we have this nice formula there. Okay. Why am I doing this? Why I keep on doing this matrices? You will see. If you all got that down, okay. If what I do now is the following. I will then insert into here dy dt, d of x dt. Okay? I've just replaced this side here to equal that. So if you look at all this, what is result? You will see the first one is essentially dy dt equals ayy times y plus ayx plus x times x. That one there. Now if I compare that one to this one here, ignoring the u term, it's just that, right? So the connection ayy, oh sorry, it's there, wrong way around, it's there. And ayx is minus 0.1. So I now have a way to have a connection matrix which describes connections to describe this dynamical system in this way here. Okay? And this bottom one, dx dt equals y, this one here. We know that axx equals 0, we had before. That's not there anymore, therefore we just have axy. That's plus 1. Yep, does that make sense? Anyone confused? Tell me right now, because they're going to get a little bit harder for me. No? Okay. Good. Okay. Now we have that. In summary, what does this all mean? In summary. This means the following. We can write, by having these two definitions, okay, we can write the following. dz, sorry, I meant to be a little squiggly line, which means a vector. dz dt. Okay, I take a dt of both terms to make it like dt on each of these. Equals a times, that's what we have now. So I can put it to the bottom here. So so think about that for a second. So what this means, it means if we have A, which determines the connections with dynamical system, and if you remember, if you're reading DCM, this is the start of the bilinear model. So we know what A means. Okay, and we had before the diagonal terms, these ones here, they determine self-connections. And as we saw, if we had these as minus, so like this minus term here, or like in the state dependent term, we have a decay. Yeah? So we have a decaying system if we have the diagonal elements be less than 1. And these other terms, these ones here, they describe the coupling terms. You can get oscillations that way. So when you have a DCM matrix, you have an A matrix, this is what it means for this first term of the bilinear model. Okay? Good. So normally when you read this literature, or read a lot of stuff, you do the following. You kind of have this system, a very complicated one, and you dissect it going through. We've done the other way around. We've started with a dynamical system and try to write it in a way that looks like a DCM. Okay? And if you're doing resting state DCM, the spectral DCM, this is as far as you get, essentially. Plus the stochastic term, which we won't go through today. Yeah? So this is a DCM right here. This is what it looks like. These are what things mean. Okay. Good, good, good. Anyone else happy with this? Unhappy? Please, any questions? Keep going. I'll keep going and if you have no questions. Now the next part is we have no input. So in the resting state DCM, you don't have any inputs to your system because you're just letting it evolve dynamically. But we're missing out U, aren't we? U's not even there yet. Okay. So what do we need? We let it on purpose out because we need a connection matrix that go from all the inputs to all the connections. This is what we do. Same kind of thing. It's the same trick, same language, same tricks here. We can make a matrix C. Okay? We want to take the connections from the inputs to the regions. So the C matrix will have the following. Always in DCM, always. The rows along this direction are always the regions. Okay? And here along here are the inputs. So for instance, input here can have another input taking more populations, another input can have as many inputs as I want. If you have a system where you have like a visual simulation and a motor simulation, you have two different inputs happening. You can have something like that. Okay, so because before we had A times Z, so we need a vector. We don't use the region vector. We have another vector, we'll call it U. Okay? And U has all the inputs. Okay? And here we'll write the same formalism. We'll have on region, we'll call it X and Y. On, YX. Let's keep consistency. YX. We have on region Y from input, call it U1. That's one entry in the matrix. Next one we have CX, so we have U1. The next row, column, sorry, we have CY, U2, CX, U2. So from U2 to X, or to X from U2. Okay? So if yes, it's the same thing we did before. Instead of having regions we now have for that one. Regions, we have regions and inputs.
What if you only have one input, like,
That's right.
so that's just one input, B1 to B2?
Exactly, let's do that now. So if we have one input, I'm not going to write this out because let's not take too many shortcuts. If we have one input, I'm going to do the following. I'm going to make U, just for consistency, make a U1. We call it U1.
Yeah.
Now this, what does this turn into? We have C equals C Y U1, C Y X U1. We have a smaller matrix, just end up in a vector. Well, it's still a matrix before, and that's still a vector. This is for our example here. We'll call it U, or it can be called U1. We'll call it U1 or U. So now if we do the following, if you do C times U, same trick, we do the following. It's, hold on. Okay, hold on. If you got all this down, I'll put it up here. Okay. I need like 4 whiteboards.
Yes.
Okay, so if I do this, if I do C times U, that equals the following, for our system only, C, Y, U1, C, X, U1, times phi, U1. I've just put these two and put them together. Our trick again, how to multiply matrices. It's that, nothing else. So it's C, Y, U1 times U1. Yeah? Next one. That, nothing else. So it's C, X, U1 times U1. Okay? Yep, all good. Now, let's put all of this together. This is going to be a messy matrix, but you'll see. So, if we do the following, if we do dz dt equals a times z plus c u, it equals the following: dy dt dx dt equals a y times y plus a yx times x, a xy times x plus a xx times x plus c y u1 times u1 c x u1 times u1. Okay? And now what we do is, what is this C value? What is this C matrix? Can you tell me what is, looking at a diagram, what do these values equal to? What is the first one? What is this connection?
0.
The first one, C. So 2y from u1.
1.
1. Next one, looking at x. 2x from u1. 0. Correct. So we can describe this whole system, this diagram, 3 different ways. We describe by this differential equation. That's way 1. Way 2, we can describe it by this line diagram. Okay, they all mean the same thing. It's all in a different dialect, like I said. The third way is via these sort of shortened matrix form. This one here is plus CU. Right, this bottom part here. Is that okay for everyone? Okay, so this we're building more and more of the DCM. If we were to have no modulation, all we had were intrinsic connections plus an input. This is all you would need. Okay, this is a DCM which isn't really used much, but you can use something like this. Okay? All right. Hold on to your hats. This is where it gets a bit more confusing. I'm going to close it off with this one. Trying to get serious. It's quite distracting noise. Okay, the last bit of this. Modulations. Modulation. So, it's all done, everyone? Yeah? Okay. So, you might have seen in the DCM papers, there is a B term. Yeah? And you see before in the first lecture we talked about modulation, modulatory terms. There we go. That's it. So what do these mean? So in the context of this frog case, we can do the following. I'm going to take this further. I'm going to include another input here, U2. Okay. I'm going to say, posit, and we have the following situation. When I'm adding more mosquitoes, I'm literally having my hand in the mosquitoes, okay? I'm getting bitten as well, but that's okay. When this happens, I'm going to posit that mosquitoes are getting slower, and they're going to get eaten faster, okay? So this is going to be my modulation. So I'm going to say the following functional form. U2 here. I'm going to say at 5 seconds as well when I'm adding things in. Okay, I'm going to say the rate of change of mosquitoes is decreasing. They're getting eaten faster because of the frogs. Sorry, the mosquitoes are getting eating faster because they're slower. And at this point in time, only this point in time when I'm adding things in, we have this modulation term that the rate of frogs eating them is going to increase. Now another way you can think of this is if I'm in a neural system, I'm looking at the visual field, and I now have a tension. It's known in a lot of cases that if you have a tension, you change your inputs from V1 to V2. Or you also have these top-down influences coming on. So this is what it means in the neural context. In this frog context, I'm talking about, it's the same sort of idea, but I'm changing one connection here. The connection I'm changing here is, I'm going to go for purple. Let me know if you can't see this, Nigel. So what this is, I'm going to add this arrow here. Can you see that? Okay. All right? This arrow here. And what's normally done in literature, when you have a modulation term, you have a dashed line. Okay? So I'm going to say that this connection appears, okay, when you have this modulate, this extra input U2. All right? Now what I'm going to call this U2, I have it here somewhere. Okay, I'm going to call U2 this. I'm going to call U2. So you need to copy this down because I will have this set as the homework thing. So once you've simulated the first thing which I showed you at the start of the lecture workshop, whatever you call it, I'm going to add another pickup to it. What I It's a minus term here, you can see here, it's minus. That's U2. And I'll put that. Okay? What I'll also say is that this connection from going to y from x modulated by U2. Okay, this U2 makes this connection and modifies it. Okay? And I'll also say 2. The strength of this is 2. Now let's go and think about this in this language here. So this language, what do I have to add in the first term here? Get someone thinking. I'm going to write it here bigger so we can all see. dy dt. Okay. Yes, that's right. So I'm going to go through why that is the case. Y plus u1 to t. Okay, I want to add something. I'm going to add, as I said before, this here is modulating this connection. And this connection before, like this one here you can see here, it's minus 0.1 times x. So that connection, because of this one. Again, it's because of this one I have it onto here. So of course I have to have x. I said it's 2. And why it's modulation, this actually comes in here and modulates it, and also another way you can say it is to times it. Okay? It's modulation here. Wasn't in this context, that's what it means. So as I said before, we have languages, right? A dialect. This is a dialect saying this modulation is like this, in this form here, I'm going to add that here. I'm going to keep this up. 2 times u2 times x. Okay. Now I want you to try, if you get stuck, just ask me, to try to simulate this system now with. So the same one we had before, same one we had last week. This homework this week is to add this term first, simulate it. Next step is to add this term, simulate, with the following conditions. At t equals 0, y equals 0, x equals 0, delta t again is 0.1. This is part 2. There's only 3 parts of today's homework. The last part is actually the easiest part, so yeah.
Can I ask where does the 2 come from?
The 2 come from, okay. I said the connection strength of this modulation term, I'm going to add 2.
Okay.
Yeah, I put it in there.
Okay.
Yeah. And you can see when you do this stuff, you sometimes don't have this extra term 2. You might just equal to 1. You put all that modulation in U2. But the reason why you want to have that 2, it's a good question actually, is you can say, can you imagine the following? So don't copy, you can copy this if you want to. So let's just say we have these regions, right? We have all the time create connections, blah, blah, blah. And let's say we have U1 modulating this term. Okay? But let's say we have U2, this inputting, not modulating, inputting. And we have this attention paradigm where you will do this. Okay? You might have attention or modulation being a strength C1, but you also might have this as well. That one there at a different strength. So the attention or modulation or condition changing affects different areas differently. And in a DCM, you try to estimate this. So these diagrams get messy very, very quickly. If you see a lot of them, they get very quick. It's hard to actually make them nice. I mean, you can use different algorithms, whatever, but what it all means is this type of abstraction, what's happening there.
So if you have a second modulation, you just add the second term to the equation.
You can do something like that, yeah.
Yeah.
And we have this term here. So we have this way representing it, this way. Now I have to add it to this. And add it to this is the hardest part of this whole bilinear model thing, because it looks messy. But if we break it down, it's easier. And what we want to do is add, like I said, this term here into this matrix formalism, and we're going to do that slowly, okay? Because this is, I would say it's the most confusing part, and when I first read it, I also got confused. So yeah, this is homework 2. Yeah?
What's U2 now at the time 0?
So U2 times 0 is just 0. It's actually this function here. So U2 and U1, they're just input terms that we put in. So they don't need this extra condition thing here. You just add a function. So as you can see here, U2 at 0 is just 0, and U2 at 5, it's it's 1 minus 1. Because you put 5 into there, 5 minus 5 divided by 4, exponential of 0 is 1, 5 minus 1. It's that there. But this is just input. This is input 2. And when you do this type of modeling as well, you normally have a task Q, and you might have attentional modulators as well. You call U2. So these two you're always inputting into your system. And what you want to do is estimate all these connections. Okay, now, rub this out. Yep. Let's talk about how to put this in. Okay, so the machinery we want to have a matrix B, the B matrix. B. So what do we want to do? As you can see here, this modulation term is affecting the connection. So somehow we want something a matrix which captures these connections, and then we want to modulate them. So the matrix we can design is the following. We have a matrix, and it will have the following properties. Here we'll have regions, and here we'll have regions as well. So like A, it's the same kind of form. It describes connections. And what we're doing here, instead of the black ones, all we're doing now is describing the purple ones. Just one. Okay? And the way it's done, and for this case, is that you don't just have one B, you have multiple Bs. But let's first start with this one here. So we'll call this now B2. Okay? And the entries will be like that. This is what this means. This means this is a connection matrix describing the modulation of input 2 to region Y from X. This is also called a tensor because it's a three-dimensional matrix. Okay, so modulation due to input 2 on Y from X. So it's quite a mouthful what this is. So what do they equal to? In our case, we have regions Y, we have regions X, we have regions Y, we have regions X. Just laying it up at this point in time. So we have here, the first one is B2, Y, Y. Next one, B2, 2Y from X. B2, 2X from Y, B2 from X to X. Is it so far all right? Okay, now let's add some complexity to all this now. Oh, not really, not really. Oh, it's scary. It's not complex, it's actually quite nice now. So again, we're going to do the same trick. I'm going to let Z equal to Y and X. Yep. Let's do B of 2 times Z. That equals. I'm getting to write this down all the time because it's just helpful so you can understand matrices. X, Y, B2, Y from X, B2, 2X from X, times Y, X. Okay? What is it equal to? Now I'm going to rub this out now. Have you all got this bottom part? Okay. Okay. This equals, again, that sort of stuff. So B2, Y and Y is going to sound pretty crazy. Y plus B2, Y, X, X. That's the first one. Second one, B2, X, Y times X. I'm running out of breath here. Plus B2, X, X times X. What a mouthful. Okay? Yep. So now we describe the connections, and then this just looks like A when we do this thing here. There's one thing missing here. We still don't have U2. Now, as I said before, this whole matrix gives me the also connection due to U2 on all these connections, okay? But all of this, if I do the following, if I do B2, Z, I times both sides by U2. Okay? they all get times by U2. So by all I mean the first row and the second row. There's a lot of equations today, but I mean, hopefully you can have an appreciation of different forms of way to write all this together. We're dissecting all of them. So once we have all that, we can write the following. So as you can see here, well, first off, before we do anything else, what is B2 equal to? This diagram. So what is B2yy? So if you put up 2y from y, what is that equal to? Just purple arrows, what do you have to look at? Just y. I mean, is there a connection from y to y that's purple? No. 0. Again, purple arrow, this one here. To region y from x. Is there anything there in the purple? And what is equal to? 2. That's 2. Next one. B2, 2x from y. What is that equal to here? 0. Last one. B2, 2x from x. Nothing. It's a very simple equation, a very simple matrix. It only has one entry because we're only changing, modulating one link. Okay? All right, good. And if you put all this together, if you put this here into here, I will show you. BZ2 times U2 equals, all this stuff together, that's gone, but that's there. So we have 2 times x times U2. Next row. That is 0, that is 0, equals 0. And what do we have here? Look at this top row, it equals this one here, the first variable. So now we've designed a matrix which can encapsulate the modulation terms. So we have all this, you go back to the last equation, plus that, we end up with this system here. For completeness, I want to do this. For completeness, let's put all this together. Okay, it's going to look very messy, and I don't apologize for it. Okay, so it is the following. First row, dy, dt, dx, dt equals. So a y times y plus a y x times x. Second one, x from y times y plus a of x to x from x. That is what this term is equal to, a times z. Plus, remember it was c is equal to c of y u1, c of x u1. But now because we have 2 inputs, we have to take care of that because that u vector has 2 of them. So I must remind you, if you take u, it's on this direction it is inputs, this is regions. Okay? I'm just going to show you what it is. We're not going to go into it too much. So it's c of y u1 times y plus c of y u2 times u2. Next one, it's going to be c of x u1 times x plus c of x u2 times u2. That should be u1, sorry. Okay? I think you should convince yourself this is what it equals to as well. plus the last term, it is b2y times yu1. Sorry, no, oops. There's only two. y u1 times y plus b2yx u1 times x. And also b2xy u1 y plus b2x x u1 times x. So given A, B, and C, in the most general form, if you have any numbers for these, this is what it equals to. Okay? Another way to say that is the following. Hold on, let you write that one top. Okay, it is the following in the most. Okay, see dz dt is equal to a z, or we had before, plus c of u plus b to z u. Oh, wait, hold on, wait. u1, u2. And that should be, I feel like my old lecture is 2. Sorry, because remember it's influence of u2 onto the connections. It would be 2, 2, 2, 2, 2, 2, 2, 2.
Order the C of y u1 times u1 or
This is also wrong, thank you.
um,
Oh, well, no, that's right, and that's
no,
right.
the one above, where C of y u1 times.
Times u1. Yep. Good. Means you're paying attention. Okay, I'm going to add this to this here. Well, I'm not going to add it yet. I'm not going to add it yet. So this here is pretty much almost the bilinear model you see in DCM. Almost. There's one thing missing. More terms. All right. This is the last crazy thing I'll show you today.
Can I
Yeah.
ask, is there a reason why you use like B2 as a superscript rather than a subscript? Or?
Yeah, that's right. There is. So the reason why you do it in a superscript is because if you didn't, you'd have like R1 or RI, RJ, another one here. And typically, most times when you have, because these are all different matrices, and it's just convention to put it up top.
Okay.
Yeah. It makes it look like it's almost squared, which is very confusing.
Yeah, true.
It makes it look it's much more complicated. It's not, because if you have a squared term, a lot of these things will look more complicated actually. And squares and differentials are actually become nonlinear, become quite hard to solve. So it's not squared. It's very confusing, I agree, for that point. And actually, I think one of the papers uses a subscript and it becomes really confusing. So I could have got used to this. Okay. Now, in the general case, I can do the following. I can say, instead of is equal to that thing there, I can say, easy. Let's say we have u is equal to u1 to un. Okay? I just keep adding them. Okay, I'll just add b1 here. b1 doesn't exist, it's always 0. But I can add b2, zu3 plus b3, b4, zu4, sorry, because u is a vector and this is it, sorry. Plus, you can see a pattern, right? This is a pattern. The way to write that mathematically is using a sum. Okay, so all this, I'm going to write it this way. Equals A Z plus C U, okay? Plus, if you haven't seen this before, be prepared to see something. Well, I love this symbol, I must say. Capital sigma, everyone's seen this before? Yeah? J equals 1. It's described this way. B of J times U of J until N. And at the end we have Z. It's normally written this way. Okay? Now this here is the bilinear equation. This is the full deterministic DCM equation. It was there in the first paper, it's always there as well. And this is the DCM equation. We've gone from having this sort of frog model in this very simple case, but in the end, we've added more and more things. We added not just self-connections, we added cross-connections, coupling, right? Which made oscillations. The self-connection we had also this decay. We then added this input term, U1, to input to the system. We then went further and added a modulatory term, U2, with modulated connections. And this is all now in here. So in fact, all those models can be described by this in the most general case. But for instance, if we want to make neuromodulation, this B's all become 0. Okay? So this is like neuromodulation, that's B becomes 0. If we want no input, C becomes 0. So in fact, we solved the equation like this for a particular A for the homework example. Alright? So we've done this before, this is just now in an abstract form. Another dialect, I'm going to add it to the bottom, how else we can talk about it. It is the sum of Bj, j equals 1, Uj times C. So 3 different ways to describe the full DCM model.
So in fMRI last lecture, you said we usually don't do modulations because it's too computationally hard.
So this here is actually quite hard to solve when you do all this stuff together. So when you want to do network discovery and all the stuff I do Razi, there's really cool stuff. Adding these terms and this term makes it quite hard. By just having this term here, it makes it much computationally more simple. So to simulate this whole system with the noise term, which I haven't introduced for by next week, it can take days to run. With just this term and cross-spectral DCM, it can take seconds. This makes it very, very complicated because you can imagine we have all these connections and all having like these competing effects. We have oscillations, we have a decay, we have these input terms, we have modulation. All this stuff takes a while to actually converge to a solution. Because in DCM, you don't just actually simulate one. You do it multiple times. You change the connections to find the optimal fit. And that makes things go wild, absolutely wild. Okay? And that is a bilinear model.
Why is it called bilinear?
Good question, good question. It's linear because of this and this. Bilinear this term here, because we have linearity in one direction, in terms of connection times this, and linearity in this term, because we have the modulations of the inputs affecting just the connection string. We don't have any other complicated relationships. It's sort of bilinear, that's why they call it. It's bilinear because of this, and linear because of this.
Right.
And I think I'll start next week just saying why this can work, why it even makes sense to use this formalism. Okay, that is like essentially most of the stuff. I'm going to talk about one last thing, which is just a homework example. So what I want you to do, this last one is no simulations, it's just pen and paper, and this isn't equations either. So So I want you to draw, as I said before, I want you to draw the following wiring diagram. It is the following. So it is U is equal to U1, U2, U3. 3 inputs. C is equal to 1, 0, 0, 0, 0, 0, 0, 0, 0. A is equal to minus 1, 0.2, 0, 0.1, minus 0.5, 0, 0.7, 0, minus 1. Okay? So this modulation term, B1 is 0. It's always 0. I leave there at 0. B2, the second one. And so these are normally quite easy because they're in terms of they're not too complicated. You don't have too many modulations. And B3 is equal to 0, 0, 1, 0, 0, 0, 0, 0, 0. So by this, we already have a DCM, a model, okay, if you're in this form. I want you to use all these matrices and draw a wiring diagram. So okay, let's remember what all these things are. Let me just refresh you. We'll talk about this again next week. U is a vector of inputs. C, this is a connection matrix detailing how inputs relate to regions. A, this is the matrix which details the self-connection. It was also called the intrinsic connections. And the last one, B, this is a matrix that details these modulational connections, these conditional connections, which only appear in the context of their respective inputs. B1, which we'll draw that again. B2 is the connections which are changed because of U2 input, the modulated term. B3 is the connections changed because of the modulated term U3. These are, I think, quite important and quite a neat idea because sometimes you might have a neural network, right? That you have like going from visual cortex to something higher cortex, and you only have a connection appearing because you're doing something else, like attending. Okay, and that's it. That's 3 homework examples. The first 2 should be related. The last one, I think, is probably the most useful. If you don't want to do 1 and 2, you make me sad. But try, please. But the last example is the most important because this is stuff you'll be using in a DCM. And thank you for your time. And next week, spectral DCM.
Yay.
Which makes the B term and C term 0. We'll be talking about what a stochastic DCM is, how it's different. We'll be talking about the observation models. These are all the neural models which detail causality in these connections. The observation model. And we'll just talk about them, but not really care too much about the equations. Okay? And then that will be kind of the end of this sort of style of things here. And after that, we'll be doing more group stuff where people can present various parts of data, and we're doing some kind of data analysis together. And money volunteers, Linda and Christina volunteers. Okay, thank you all. Sorry for going over time. Enjoy.